Section 8.5 is power series, and this is our first time dealing with a variable x in our series. And this is um, one of the major steps towards our ultimate goal of representing transcendental functions like e to the x and arctangent of x and things that are not polynomials as infinitely long polynomials. So a power series has the given form we have here. I have a coefficient c sub n and x to a power of n. So we start at n equals 0, or that might possibly change in the future to n equals 1 or some other arbitrary index. But generally, it's infinitely long. There are infinitely many terms that we'll have. So there's a coefficient for each one of our terms, C1, C0 through C3, and so on. And then those are each times x to its respective power as we step out in the series. So we already actually know a power series that we're going to get to pretty quickly here. But I want to restate what I said to open in this video here below. Any function or not, so a power series for some function, we'll say for now, some function f of x, can really be looked at as an infinitely long polynomial. Each of these powers of x is a positive integer power of x to the first power into the 0th power for the last two here. And that being the case, and we have real number coefficients, C0, C1, C2 times all of these powers of x, this makes this a polynomial. It's just infinitely many terms in it. Now, polynomials are really easy to work with. That's why we'd want to represent some given function, no matter how messy it might be, tangent of x squared or arctangent of x, arctangent of 1 over x, things like that. We'd like to be able to represent something like that in terms of a polynomial like this, so that maybe we can approximate things better or do easier calculations with such a function. So, like I said before, we've already seen one of these power series. The most simplest power series we can come up with is coefficients equal to 1. And then we just have 1 plus x squared plus x cubed and so on, plus x to the 4th plus x to the 5th. And really, when we think about what that is, that's the geometric series, where our series term will go from n equals 0 to infinity. Our series term is just x to the n. Well, we know that this is convergent. It's equal to 1 over 1 minus x whenever the absolute value of x is less than 1. That's the geometric series entirely. So now instead of having r, we just have an x in our series definition right here as our ratio, and we immediately get our very first power series. And we'll actually base a lot of what we do off of this power series in the future. We'll build new power series from old in the next section, and we'll start with the geometric series to do so. But before we get there, we should talk about the radius of convergence and the interval of convergence for a power series. In other words, we note that this geometric series, or this power series that we've given here, only converges when the absolute value of x is less than 1. So to sort of introduce its radius of convergence, we'd say that it converges whenever x is between -1 and +1. And these are parentheses. This would be the interval of convergence. So there's no work to do for this one because we've already done that. We know about the geometric series. So it has an interval of convergence from -1 to 1. So we're still connecting to this old idea. We're going to connect to the newer concepts of intervals of convergence for a more general power series momentarily. But this is a nice tie-in point for this. Now, there's one more thing about this series we can note. It has a center. And the center is really the center of this interval. That center in this case is 0. 0 is the center of this power series. So that's another thing that we'll note. We'll see that in our analysis to come. And I guess lastly, one thing we could say is that when we look at this, we see that our radius of convergence is the limit, is the distance x can be away from its center, right? So if x can be as large as +1 or as little as less as or small as -1, then we know that its radius of convergence is 1. So radius of convergence equals 1 in this case, kind of scribbled in there. So these are all the parts to a power series, and that's primarily what we're interested in this section. So let's have a look at the more formal take on all of this. So the general power series definition is the following. The only thing that's really changed here, other than the coefficient in x to the power of n, is the fact that we're dealing with x minus a now. So the center of this power series is a. So if we go back and look at the previous one, for this power series, the center of such a power series like this would be 0, right? Because we can rewrite this series term as c sub n times x minus 0 to the n. So there's sort of an understood minus 0 in this format. And that's how we know the center of this one is at 0. Okay, so it's a special case of the previous, or the formula on the page we were just looking at. So here's our general form for power series centered at A. Okay, so that's always pretty much always easy to spot. Now, whether or not one of these series converges is a great question. So we've got 3 different things that could happen if we're given a general power series. It will only converge, so this general power series might only converge when x is equal to a. Okay, so this series might only converge when this is the case. Now, it's guaranteed that that at least happens, right? Because if we put x equals a into this power series, then we just have a minus a. So we have 0. We're adding up 0 infinitely many times. That, of course, is equal to 0. So this thing would converge. Now we're thinking of this power series now as a function of x. So f of a would be 0 if we were to plug that in, because as soon as we put an a for x right here, all of our terms collapse to zeros to some power, and that's 0, and then they all sum up to 0. So that's our first case. That's the more basic thing that could happen, but we know that our function should at least converge at its center. Our power series should at least converge at its center. The next thing that might happen is the series might converge for all x values, for all real numbers x. Doesn't matter what we plug in, it might converge. Okay, it's going to be our task to figure out which of these 3 cases holds, by the way, general power series that we look at. The third possibility is the more complicated one, and that's there exists a positive number r such that the series converges if x minus a is less than or equal to r, and it diverges if x minus a is greater than r. Now what that leaves is what happens if x minus a is equal to r. So it may or may not converge at the endpoints as well. So I didn't include the non-strict inequalities or the weak inequalities in this notation here, because that's up for grabs, and you'll have to check it case by case to see whether or not we include an endpoint or not. So we might have an interval that goes from a minus r, the center, all the way to the left, 1 unit or 1 radius unit, right? Plus the center, or all the way up to the center, plus a radius to the right. Okay, so remember in our previous example, the geometric series, we had a was the center for the geometric series as a power series, and the radius r was 1. So then our interval of convergence comes out to -1 to 1. Okay, now in the case of the geometric series, we know that we don't include these endpoints. We've seen that. That's been proven to us in previous work, so we know they're not included. In general, power series that we'll look at, it should be typically easy to come up with the radius of convergence. It's very easy to spot the center. And lastly, to put together our interval of convergence, since we can come up with the radius, we just add it's 0 minus 1 and 0 plus 1. And that's how we get the interval of convergence right here. Okay, a minus the radius, a plus the radius. The last thing we'll have to do in detail is check each of these endpoints to see whether or not the series converges as a standard series, not as a power series anymore. And then we can determine whether or not to use a parentheses or a bracket. But of course, for the geometric series, we know both of those need to be parentheses. Okay, so those are the 3 cases. It will only converge at its center, converges for all real numbers, or it converges for some finite interval on the real number line. So to see our first example, we're asked to determine the radius and interval of convergence for the power series. Well, this is again the geometric series. This is an interesting thing to do. We already know this, but this is a nice confirmation maybe that our workflow and the typical algorithm we use to establish radius and interval of convergence is actually true. But we'll apply this to the geometric series just to see that. Now, the ratio test we'll typically use um, as follows. We'll say the limit as n goes to infinity of the n plus 1 term divided by the nth term. So n plus 1 term divided by the nth term. Remember that's always our ratio. What we'll do is we'll take this limit, with the absolute value, of course, and we'll impose the condition for convergence in the ratio test. And remember that series only converges when this limit is less than 1. So typically we'll write this limit down and we'll work to the right until we've evaluated the limit. And then we'll write down what our condition for convergence is in the ratio test. So in other words, we'll just write less than 1, strictly less than 1 after this. And we'll check to see what x values this side satisfy that less than 1 relation. Well, in this case, the absolute value of x being less than 1, well, that's exactly what we know about the geometric series. That is the condition for convergence of the geometric series. We've just written that in terms of the ratio test. So the radius of convergence in this case is r equals 1, right? Nothing changed from here to here. So if we had a constant times the absolute value of x, then maybe that would have changed things a little bit. So our radius of convergence is r equals 1. We already knew that just sort of by inspection previously. Now our interval of convergence is the center minus 1 to the center plus 1. So we have negative 1, 1. And the question is whether or not we include or exclude the endpoints. We didn't deal with that in detail in the previous page. We've probably seen in the past that that's not the case, or what the case actually is. But let's go ahead and look here more individually or more specifically and see what the results are. So when we look at x equals negative 1, so we're swapping out x with negative 1, and we get this numerical series type of thing that we've been dealing with for a while now. But when we look at this series term, we realize that if we take the limit as n goes to infinity, it's going to oscillate between negative 1 and 1. It doesn't converge to 0 as n goes to infinity. That being the case, this thing diverges by the divergence test. Okay, so we're able to show that. So this one is not included, so this parenthesis should stay a parenthesis and not become a bracket. When x is equal to positive 1, we have 1 to the n. Well, that's actually just 1 in that series. So we're adding up 1 infinitely many times. It's pretty easy to see that it diverges. But if we take the limit of this series term as a sequence, we're just taking the limit as n goes to infinity of 1. Well, that's 1, and that's not 0. So again, this one diverges by the divergence test. So also, we don't include the positive 1 on the right because it's divergent as well as a numerical series here. So exactly what we expected and already knew is shown by our new technique here. The key is that we use the ratio test, impose its condition for convergence, and then assess which values of x satisfy that. Okay, so the question in this case is, well, won't this always be the same if the series looks like this? Well, in the case of this geometric series, yes, but let's say that we arrive at this point that's highlighted right here, absolute value of x, and then we impose our condition less than 1, but we get something different than just absolute value of x. This is quite possible in problems that we'll see in the future, and likely. So we've gotten to that point. We've taken the limit of the ratio test, and we get 7x as our absolute value of x. So in other words, imagine that this point here is an absolute value of 7x. We impose our condition of less than 1, and now we're asking what's the radius of convergence in this case. Okay, so that's followed down here. So we have our absolute value 7x, that's our limit of our ratio. We don't actually have a series here, we did a shortcut just to get to that point, just to see what would happen. We impose our condition for convergence of the ratio test, in other words, that thing has to be less than 1. And maybe to go a little further, this is the part that we didn't see or do. The limit as n goes to infinity of c sub n plus 1 over x to the n plus 1 over c sub n x to the n came out to be equal to this. Just to show the extra details, that's what our limit of our subsequent and previous terms came out to, was that absolute value of 7x. And then following our workflow, we're imposing the condition that this thing is less than 1. Okay. Now, really, we're just dealing with this part. That's all that's interesting. We have the absolute value of 7x, strictly less than 1. And, well, 7 can factor out of there, leaving us with an absolute value of x. And then, really, the goal is this every time, is to isolate the absolute value of x. Okay, so when we were here, we knew that we wanted to isolate the absolute value of x, because we want to know how far to the left or how far to the right we can go. It could also be the absolute value of x minus the center. In this case, it is the center. 0 is the center, x minus 0. But it might be something else in the future. We'll see what to do when we get to those examples. So having done so, we see that the absolute value of x is less than 1/7. Our radius of convergence then is 1/7. Okay, so really the general trick is to find a coefficient in front of x inside the absolute values, get it out of the absolute value, and then get it off of this side completely. So we want just the absolute value of x, or the absolute value of x minus some constant. As soon as you've got that on the left-hand side, you look to the right-hand side, and you've got your radius of convergence right in front of you there. So r is 1/7 for the radius of convergence. Our interval of convergence now is negative 1/7 to positive 1/7. Again, because our center is 0. X minus 0 is in there. So that's our interval of convergence in this case. So continuing on, let's find the radius of convergence and the interval of convergence for this series. N equals 1, n to the n times x to the n. So same thing, we apply the ratio test to the subsequent term and previous term, a sub n minus plus 1 over a sub n. Limit as n goes to infinity, absolute value of all that. So this is this expression replacing an n plus 1 everywhere we see an n. And then this is just the same expression, a sub n, or c sub n x to the n. The center of this power series, by the way, is 0. So it's good to keep track of that. There's no x minus a number or x plus a number to a power of n. It's just x to the n. Now, proceeding with the work we've got to do here, we've got n plus 1 to the n over n to the n. We group these terms and try to make them look more like each other. So what has happened here, we've also taken the x terms and factored them out as their own ratio. We've taken one of these powers, n plus 1 to the n plus 1, and we put a first power of it off to the side. That way, the exponent of this term and this term match. So if we look at this n, we realize that there's a 1 here, and then if we were to multiply these two terms together and combine their exponents, we'd have n plus 1 again. So we're just being a little tricky with exponents here. So in doing this, though, and setting this up to have the matched exponents, we can now write this ratio to the power of n. So in other words, we have this all to the power of n, and that is taking only this part of this expression to do that. And we're left with an extra copy of n plus 1 right here. Okay, that comes from this term. So we can simplify a little bit inside those parentheses to the power of n, and we end up with 1 plus 1 over n to the n. And then we have times n plus 1, and then times x. Well, x doesn't go away in this limit, right? That's the one thing to remember. We're not taking the limit as x does anything. We're taking the limit as n does something, okay? 1 plus 1 over n to the n, well, I'll let you guys look that up. It should be something like e, or e to the negative, or e to the 1 over n, or something like that. It's going to be an exponential. At any rate, it's a finite number. This one, on the other hand, n plus 1, as n goes to infinity, runs off to infinity. So this is driving the entire expression to be infinitely large. And that being the case, we have that the limit is infinity. Now, if this limit is infinity, well, the ratio test needs this limit to be less than 1. Well, infinity is certainly not less than 1, so this thing doesn't converge anywhere except for its center. It converges at its center, which was 0. So it has a radius of convergence, which is 0 because there are no x values. So this ended up being, didn't matter what x was, there are no x values that will make this less than 1, except for 0. So maybe I'll make a mention of that. I'll be more clear about that, except if x is 0, right? So we do have that one exception. So its interval of convergence is only its center. Otherwise, everything else drives this expression to be infinity, which is not less than 1. So we don't have any kind of convergence outside of our center. So there's the summation of the results for that, the summary of those results. Radius of convergence is 0. Interval of convergence is just the center, or the set containing 0, or the set containing whatever the center is in a more general problem or power series. So another one, determine the radius and interval of convergence for the given power series. So this will just sort of repeat itself through all of this section, just getting a lot of practice with these things. We have x to the n divided by n factorial. It's interesting to write this out and have a quick look at it. When n is 0, we take x to the 0. Remember that n factorial, 0 factorial is 1. So we have 1 over 1, and we just get 1. When n is 1, we have x to the first over 1 factorial. That's just x. When n is 2, we have x squared over 2 factorial. And then so on. We're adding all these terms up as this power series. So we have an infinitely long polynomial that looks like this. Of course, that doesn't do anything to find the interval of the radius of convergence. It's just, good to see what these things are, because we will be dealing with them and thinking of them more or less as this infinitely long polynomial and doing operations with such things. So now to find its interval and radius of convergence, as always, it's the ratio test. The limit as n goes to infinity of the absolute value of the ratio of one term over the previous term. So a sub n plus 1 over a sub n. Okay, and when we fill that in, the first term, the term in the numerator, is x to the n plus 1 over n plus 1 factorial. Remember that the game there is to swap everywhere we see an n in this expression in the series, x to the n and n factorial, with an n plus 1 and n plus 1 factorial. Okay, and then we divide that a sub n plus 1 term by the a sub n term, which is usually always just the general term that the series is written in. And now we want to group the things involving x. And well, first we're handling the division here. So we're multiplying by the reciprocal of the second fraction, or the denominator fraction. And then we group powers of x and then expressions involving n. And in doing so, we see that x to the n plus 1 over x to the n cancels to x. So we have this term. And then n factorial over n plus 1 factorial. Let me pause here, actually. Be a little bit clearer about this. N factorial over n plus 1 factorial. N plus 1 factorial is n plus 1 times n factorial, right? It's nested in there. N plus 1 times n factorial. This thing here is equal to, n plus 1 factorial. Remember, because n plus 1 factorial is n times n plus 1 times n times n minus 1 times n minus 2, all the way down to 2 times 1, so on. Okay, so that's a little trick there. It's also been written off to the side here, so I'm being extra careful about it. But that's what's happened there. So what that means is the n factorials cancel to 1 here. We're left with 1 over n plus 1. And we're taking the limit as n goes to infinity of that whole expression. So x doesn't move, right? The limit has nothing to do with x. It's all about n. So this thing drives the whole expression to 0 as n goes to infinity. So 0 is always less than 1. So that means for all real numbers, this is going to be true. This thing will have a limit that's less than 1. Okay, so it's a little bit backwards, right? You'd think that when this limit was 0, you'd say that your radius of convergence is 0. It doesn't work that way. It's all about the convergence per the ratio test. If we get 0 or 1/2 or 1/10 right here out of our limit, well, then in something that's always less than 1 strictly, well, then we can conclude that it doesn't matter what x values show up. This expression has nothing to do with x, and so it must converge always. So that's the interpretation of that situation. So in this case, our radius of convergence is infinity. We see that down towards the bottom of the page. Our interval of convergence is negative infinity to positive infinity, because simply our radius is that. This power series converges for all real numbers x.